Hello, I'm Mr. Matt. Welcome to another of the AP statistics lessons, and this is specifically for the new 2027 curriculum. And today we're going to be talking about topic 1.5, graphical representations for one quantitative variable. So we're going to be using graphs to represent a quantitative variable. In the last section, topic 1.4, we used graphs to represent values or a distribution of one categorical variable. And so today we're going to be talking about quantitative variables. And remember, a quantitative variable is just a variable that takes on numerical values that are counted or measured. Okay? So we're going to start off here with a table of data. We have a frequency table. I'm sorry, not a frequency table. We have a table that shows the names of some individuals, and then the variable that we are interested in is the height. All right, the height of these individuals in centimeters. All right, so we have 30 individuals here, 30 observational units. And for each observational unit, we have measured their height and recorded it. And so today we're going to be talking about different ways that we can use graphs to represent this specific set of data. All right, the first kind of graph that we're going to learn about is something called a dot plot. All right, a dot plot. Now, what is a dot plot? It's where each datum is represented by a dot over a number line. Identical or nearly identical values are stacked up on top of each other. Okay, so let's look at an example of a dot plot. This is a dot plot for our data up here. And so you see that we have a horizontal number line. And on this number line, it lists the different heights. All right, so all the way from 153 all the way to 192 centimeters. And above some of these values, there are a dot. And each of these dots represents an individual, an observational unit from this data set above, all right, from our data set above here. So let's look here. For example, we have Wang Wei here has a height of 171 centimeters. So down here, there is above 171 centimeters here, there is a dot. This dot represents Wang Wei, or at least one of these three dots here represents Wang Wei. All right, we have another observational unit, Li Na, and she has a height of 164 centimeters. So that means that there is going to be a dot above 164 centimeters here. So each one of these dots represents one of these individuals. So that means there are 30 dots on this dot plot. Okay? And when we use a dot plot like this, it's very helpful because we can look at the shape of the distribution. Now remember, let's quickly review. What is a distribution? A distribution is all of the values that a variable takes and how often it takes them. So in this case, our variable is height, and these are all the values that the variable can take. All right, each time we have a dot, that's a value that the variable takes. And then the number of dots on top of it represents how many times an observational unit takes this value. So this is a representation of the distribution of the height variable. The distribution of the height variable looks like this. And you can see it kind of has a shape, all right? And later on in a future topic, we are going to talk a little bit more how to describe the shapes of distributions. All right, but right now I just want you to notice that there is a shape to the distribution. Okay, let's move on. So this is dot plot. It's pretty simple, very easy. The next type of plot is a little bit more complicated. It's called a stem and leaf plot, or sometimes it's just called a stem plot. All right. And with a stem and leaf plot is going to split values of a quantitative variable into two parts. The stem, which is usually the first digit or digits, and then the leaf, which is usually the last final digit of the value. Then the stems and leaves are ordered from smallest to largest. So that might be a little bit hard to understand just by reading it. So let's look at an example, and that will help us. Now, what I want you to notice is that in our original data set, each of our values is a 3-digit number, all right? 168, 164, 172. All right, these are all 3-digit numbers. So what we're going to do is we're going to use the first 2 digits as the stem, the stems, all right? So here, the smallest we have is 150 something, and then the largest value we have is 190 something. So that means our stems are going to be 15, 16, 17, 18, and 19. And then the last digit of our height is what we call the leaf. All right. And so over here, we're going to write our leaves. All right. So we have 155, then we have 158, and then here we have 162, and then this one here would be 168, and then here's 170, 175. Like we have all these different stems, and then the leaves represent the final digit of the value. And so we can see that there are two observational units that are in the 150s. We can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 observational units are in the 160s. Okay, and so on. So this is a representation of our data set again. Now, let's look at the differences and similarities between a stem and leaf plot and our dot plot. Well, the similarity is that we can see each individual is listed here. So, for example, this is the individual that has a height of 155. This dot represents them. And then right here, this leaf represents that same individual. And if we want to, we can come up here and look at our data set, and we can find the individual here that has a height of 155, Song Li, and that is this individual. And we can see that individual represented in both our dot plot or in our stem and leaf plot, okay? But the difference between a dot plot and a stem and leaf plot is that the stem and leaf plot puts the observational units into groups based on their first 2 digits in this example, okay? So, so we have here our stem for 15, and we can see that there are 2 people in that 150 group, okay? So that's the difference there. One thing that I want to mention is that when we make a stem and leaf plot, we should always include a key. For example, here it says 15 with the line, and then 5 represents someone with a height of 155 centimeters. Okay. So usually what we do when we're making a stem and leaf plot is we write the stems, and then we write a line next to it. And then on the other side of the line, we write the leaves. Okay, so I hope that's clear. Now we're going to talk real quickly about another type of stem and leaf plot. But in order to talk about this stem and leaf plot, we're going to have an additional set of data. So here I have the heights of residents in Shanghai. All right, so we have 20 a sample of 20 residents from Shanghai, and up here is an example is 30 individuals from Beijing. All right, so we have two sets of data now. Same variable. We're still talking about height in centimeters, okay? But we are two different sets of data with the same variable. Now, with these two sets of data, we can create something that's called a back-to-back stem and leaf plot. Back-to-back stem and leaf plot. And notice here it says that this type of plot is used to show two data sets for the same quantitative variable. They share the same stems, but the leaf values for one set are displayed on the left side of the stems, and then the leaf values for the other data set are on the right side of the stems. So in our example here, now our stems are the same, 15, 16, 17, 18, and 19. But on the left side of those stems, we have the leaves for Beijing heights. So there's someone who is 155 centimeters in Beijing. And then over here, we have the stem, the leaves for the Shanghai individuals. So here we have someone that's 155 in Shanghai. All right. And so if we look up here, we can see that, yes, there is someone, Ma Ting, is a 155 centimeter tall person in Shanghai. So that just means that we have someone that is the same height. Song Li and Ma Ting are the same height. They are both 155. All right, but you can see down here, we have someone that's 163 centimeters tall in Shanghai, but there is nobody that is 163 centimeters tall in Beijing, in our Beijing sample. So there is a leaf for 3 on the 16 stem on the Shanghai side, but not on this side for Beijing. Okay, so we are able now to look at the shape of the data for Beijing, and we can compare it to the shape of the data for Shanghai. All right, and that's the benefit of using a back-to-back stem and leaf plot, is we can compare two different sets of data, and we can go, we can understand how the heights of the sample for Beijing are different from the heights in the sample for Shanghai. Okay, we have one more type of graph that we're going to talk about today, and this one is very important. We use it very frequently. It's called a histogram. Now, a histogram might at first look a little bit like a bar graph, but this is not a bar graph. Bar graphs are used for categorical data. Histograms are always used for quantitative data. All right, that's the difference. All right, now what is a histogram? Well, it places the observed values of the quantitative variable into ordered intervals. We're going to put them into intervals. These intervals, we call them bins, B-I-N-S, bins. All right, and so they are in ordered intervals called bins along the horizontal axis, and then the height of each bar represents the frequency, or the relative frequency, of the observational units with variable values in that corresponding bin. So what does that mean? Well, let's look here. And this is for our Beijing residents again. And so our first bin, our first interval, is from 155 to 160. So what we're going to do up here is we're going to go to our Beijing data, and we're going to count how many people are between 155 and 160. All right, nobody here. Well, we've got one here, Shanghai, and then nobody else. And then over here we have Song Li. All right, so we just have Zheng Kai and Song Li. That's 2. So that means in our bin for 155 to 60, we're going to go to height 2. All right, so there's 2 individuals or 2 observational units in this bin. Then we do the same thing for the next bin, from 160 to 165. So we're going to come up here. We're going to count how many people are between 160 and 165. Well, we've got this one. We've got a few others here. We've got Liu Fang, and then we've got one here, and then we've got one here. And then if we look through here, there's nobody. We're not going. 165 is not going to be included. It's going to be in the next bin. We're going from the low to the high, but we're not going to include that high boundary. Okay, and it looks like that's it. There's no more. So there's 1, 2, 3, 4. So that means when we go down here to make our histogram, our next bar in the histogram is going to go up to 4 because there are 4 individuals between 160 and 165, and so on. And that's how we create our histogram. Okay, so we can see how many people are in each bin, and then we draw the height to that. Now, one thing I want you to notice is that when we draw a histogram, it looks a little bit like a bar graph, but remember I mentioned in our bar graph lesson, in our last lesson, that when we make a bar graph in statistics class, we should always put a space between the bars. The reason we do that is because that distinguishes a bar graph from a histogram. So we can tell this is a histogram because there is no space between the bars. Whereas with a bar graph, we would always put a little bit of space between each category for each bar. Okay? So notice that with our histogram, it has the benefit that we can easily see the shape of our distribution. We can see all of our variable values, and we can see how often those values are taken. Now, there is one disadvantage to a histogram compared to a dot plot and a stem and leaf plot, and that's that I cannot see each individual value. Up here, we could see that there is someone that is 155 centimeters, and we can see that there is someone that's 158 centimeters. But down here, I don't know that the individual values. I only know that there are 2 people between 155 and 160. Okay? So that's a disadvantage of a histogram. So if that's a disadvantage of a histogram, why should we use a histogram instead of a dot plot or a stem and leaf plot? Well, the reason is that if our data has many, many values, or if we have continuous data that's got decimal points and things like that, well, in that case, it will be much easier to put the observational units into bins and represent how many people or how many individuals or observational units are in each bin. And that makes things a little bit easier. All right, we don't want, if we try and do that for a dot plot or a stem and leaf plot, we might get tons and tons of dots and tons of different values. We might have 153, 153.1, 153.4, and we've got too many values, and it becomes a mess. The same thing with a stem and leaf plot. If you have too many different values, it can be difficult to deal with. So histograms are much better at dealing with large sets of data. So that's why histograms are very frequently used in statistics. One other thing I want you to notice is that when we can change the size of the bins. So in this one, my bin size was 5, 155 to 160, that's 5, and then 160 to 165, that's 5, and so on. But I can change the bin. So for example, now I've changed it to 150 to 160. So that's a 10. So the bin width is 10. And then here, 160 to 170. So that's 10, and so on. And you can count how many people are in each of those bins now. And when we change the bin width, it might change the way the histogram appears. All right. So we can see these look much different if we change the bin width. All right. Now, I just mentioned the advantages of dot plots versus histograms. All right, so that's pretty much it. We are finished with topic 1.5, and we're going to go ahead and look at some practice for this. And these shouldn't be very difficult. Let's look at number 1. According to the histogram below, how many residents in this sample have heights between 160 and 175? Well, let's see. 160 is here, and then 175 is in the middle of this bin. So looking at this, am I going to be able to figure it out? Is the answer 12, 23, 18, or this histogram does not provide this information? Think about that for a moment. Well, I hope it's obvious that this histogram does not provide this information, because although I know that there are 13 observational units between between 170 and 180, I don't know how many of those are between 170 and 175. I don't know. Maybe all of these 13 are from 175 to 180. I don't know. All right, so just looking at this histogram, this does not give us enough information to know how many we have from here to here. Okay, so the answer is D. Let's look at number 2. According to the dot plot below, what percentage of Beijing residents in this sample are taller than 175 centimeters? Okay, taller than 175 centimeters. So in that case, we're going to want to find 175 centimeters, which is right here. It says taller than, and so that's not including 175. So that's going to be these people right here. Okay, so let's see. Is the answer 23.3%, 42.1%, or 31.6%? Okay, well, or is it that this dot plot does not provide this information? Well, let's see. We have 1, 2, 3, 4, 5, 6, 7. Okay, so there's 7 total residents that are greater than 175. And how many total residents do we have? Well, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So 7 out of 30. All right. So that is going to be our proportion, or the ratio. If we want to figure out the percentage, we just need to divide that. Now, obviously, this is going to be less than a third. This looks to me to be like 23.3%. We can quickly maybe take out a calculator and we can calculate that. Let me pull out a calculator just on my phone real quick. And we get 7 divided by 30, and you get 23.3%. So that is correct. So the answer is A. Easy. All right, next, look at number 3. The following dot plot shows the number of strokes taken by 20 professional golfers competing at an 18-hole golf course. Which of the following best describes the type of variable represented in the dot plot? Is it quantitative and discrete? Is it quantitative and continuous? Is it categorical and discrete? Or is it categorical and continuous? All right, so think about that for a moment. Well, it should be quite obvious that C and D cannot be the correct answers, because this is clearly not categorical data. The number of strokes that we shoot on a golf course is going to be a quantitative number. It's something that we count, the number of strokes. And remember, if we count it instead of measuring it, then that means it is a discrete variable. So the answer here would be A. This is quantitative and discrete, right? Now, of course, there is no such thing as a categorical discrete or a categorical continuous variable. Categorical variables are just categorical. They're just categories. There's no discrete or continuous. Okay, so we are finished with this section. I hope you learned something, and we'll see you again for topic 1.6.